So, one neat thing about the specific intensity is that we can use it to also define various physical quantities of the radiation field. Specifically, what we will have is the energy density. We will have the flux, and we will have the pressure of radiation. So, for example, the energy density is just the energy density. So, if you look at again, the air in this room, the energy density here is dominated not by the radiation, but actually by the gas particles. Okay? For other systems, like what we are working on, then the total energy density of the system is actually dominated by the radiation. And even more so, it was so for the universe itself, in the early universe. It's not anymore. The energy density of radiation, on average in the universe, today is actually very low. But in the early days, it was the dominant part. And this is another thing that we will come back to when we discuss the cosmic background radiation in the course. The flux is the net rate of energy that is transported. So that's, for example, you can see the sun as emitting a lot of energy. And that's in the form of radiation energy. That's because it has a flux from the surface of the sun that's pouring out. A net rate flow of energy. Okay? That's the radiation flux. And then radiation can also exert pressure. So again, we're going to take the room. We know that so gravity acts downwards here, right? So what keeps the air from falling to the floor? I mean, it wouldn't be so nice if it did, and it actually does it. But gravity acts downwards. Why does not the air fall down? Yeah. Do we know? Sorry? Sorry? The negligible mass, yeah. Well, actually, if you think about it like this, when you go up to a mountaintop, the pressure is lower there, right, than it is here. Okay? This is something that we all know, so to say, intuitively also, you know. The boiling of water and stuff like that. Yes? Yeah, to some extent sure. But what I was actually going to here is that there is a pressure gradient. So the pressure at lower levels is actually higher than the pressure at higher levels. And this gas pressure gradient then is actually what keeps the gas here in what we call hydrostatic equilibrium. Okay? Now, for certain astronomical objects, that also happens. For example, in the sun's atmosphere, is kept together by the same process. The gas pressure, yeah, keeps it from collapsing inwards because of its own gravity. Okay? But in other systems, that pressure gradient is still there, but the dominant part comes from the radiation. Again, in some of the systems that we work for. So then it's not the gas pressure that actually keeps the atmosphere from collapsing inwards, it's the radiation pressure. Okay? Similarly, in the early universe, since the radiation was a dominant part, right, then in the early universe, you could actually emit sound waves. But those sound waves were quite different than the sound waves that we hear here. Because it was so dominant by the radiation pressure, so that they were essentially radiation pressure sound waves, we can call them, in a lack of better words. But that means that the traveling of those sound waves were the speed of light divided by square root of 3. And that's something we will actually calculate later during the course. Whereas, well, the sound waves that I emit now, they're certainly not traveling by the speed of light divided by square root of 3, right? And that's because it's the gas in this room that acts against it. All right. So that was just a few of these physical quantities that we'll define. We will start with the energy density. But first, I just need to introduce something which I actually forgot about the specific intensity. And that was that sometimes we see the total specific intensity. Previously, I set it up, and it was really within a very narrow frequency bandwidth, right? But typically, we denote that by I subscript nu, where this subscript nu then just means that we have taken it at a specific frequency or within a very small bandwidth, okay? Now, if we define the total energy, total specific intensity, then we just integrate over all possible frequencies to get out the total. Typically, then you see it without the subscript. That's the convention here in the notation, okay? Without subscript, frequency integrated. With subscript, then it's at a given frequency, or more technically within a very small bandwidth. So let's go back to our apparatus. And here we have it. And then we're going to create a little cylinder here, where we have light. And then the light was let in, right, during a T. So the volume of this little cylinder will just be the area here, area 1, times delta T times the speed of light. That's the distance. Yeah? And then we will look, what is an energy density? Well, an energy density is just the energy per volume. We had this was the specific intensity, right? Then delta T, A1, delta nu, delta omega. Then we divided by this, A1, delta T, C. Should be some cancellations here, if we did it correctly. I nu divided by C, delta nu, delta omega. So there we get our energy density, but as you can see, it's just within a given frequency, small band, and within a small solid angle, right? So again, in analogy to this, to get the total energy density, the only thing we have to do is to integrate over all of those. So the total energy density then we can define as the integral over all frequencies over all solid angles, I nu divided by C, d omega d nu. Where again, I remind you of that this is just, if you want to put it as a triple integral instead, then it is just this one. Okay. Similarly to the specific intensity, we can also choose to define it only per given frequency. That is E nu then is just integrals over all solid angles of I nu divided by C d omega, right? Such that the total then in that sense would be just E nu d nu, and then the new integral is just 0 to infinity, just by analogy. It should hopefully be clear. And then we have a good definition of radiation energy density in terms of this basic quantity specific intensity, which is a very useful quantity because it's essentially a complete description of the radiation field in the absence of polarization. So at the end today now, we will just discuss a little bit about the flux, and then we'll continue on Friday with that and the pressure, okay? So first, what is a flux? Well, I said it it's a net rate of a flow of energy per area. Okay, that's normally what we mean by a flux. Okay, so in this context then, what does it mean? Well, pictorially you can think that, okay, let's have, again, we have something like, now I'm going to put this NC, and this would be something like NX then, yeah? And now, let's see, we have a bundle of rays, yeah? We have one bundle with a magnitude 1, okay? And now we're interested in the net rate of flow energy per unit area in this direction, huh? So that would be the flux. So in this case, what would the flux be in that direction? If the magnitude is 1, what's the net rate? Well, it's 1, yeah? Okay? But now we have a second ray. And that's in the opposite direction here. In that direction. Okay? Same magnitude, 1, 1, up, down. 2 bundles of ray. One this way, one this way. What is the net flux now in that direction? Sorry? 0. Yes, because this one cancels with this one. And in this direction? Well, 0. Yeah, exactly. So this is how you can think about the flux. It's actually the net rate. So that is important. Yeah. So this is, for example, when you have an isotropic radiation field, which means that I nu here is independent of direction. That is, you have as many bundles in this way, and is in this way, as in this way, as in this way, as in that way, as in that way, as in that way. What is the flux then? What do we think? If it's isotropic radiation? 0. Isotropic radiation has 0 net flux. That's why black body radiation doesn't have a flux, which we will study and calculate later, actually. All right? Also, what you can also realize from just this schematic here is that flux has a direction, right? It is a vector. So if we now put it in this direction, yeah, we have a unit, we can call it n hat, yeah? Then, of course, if the magnitude is 1, then the flux in this direction is, well, 1. But often, we want a vector composite, right? So perhaps we're interested in the flux in the NC direction or the flux in the NX direction. Then, of course, in the NC direction, the flux will just be cosine of theta, where this is the theta angle. In the NX direction, this is sinus of theta. So just from this, we can also realize that flux actually is a vector. Now, I should say that in a lot of the astrophysics literature, you will see this more as a scalar. Yeah? And depending on the situation, then one has to figure out in which direction this actually means. For example, when you work with stars, it's often implicit that when you talk about the flux, it's in the vertical direction, right? And that is that because most of the properties, you know, go outwards, vertical in the star. You know, you think about the sun, it's a sphere, and then it emits outwards, right? So the flux comes outwards, okay? But that's an implicit assumption then in that we say, okay, the flux is in the vertical direction. We call it the flux often. But that means that everything in this direction and in this direction, they must cancel. That is, if you look at the components in this direction and in this direction, they must be equal in both, such that in the end they cancel out. Okay? And it turns out that that's, to a zeroth order approximation, often the case, but not always. When you have flows and stuff, it's not the case. But for example, here, in the atmosphere again, I like to take the atmosphere of the Earth, but also then the atmosphere of a star. To a first extent, this is true, right? Because when we look at it horizontally like this, most variables, they're constant, but we have the variation in the height. Yeah? And you can think about the stellar atmosphere, for example, a little bit the same way. So that the variations here, they often cancel out, and then you have a net variation in that. But technically, in the first chapter, we'll actually use flux as a vector here and learn how to calculate it. And when we, for example, construct our three-dimensional models of stars, well, then we have flux in all sorts of directions. Yeah? Well, in the three spatial components that we can have, of course. All right. And on Friday then, we will continue with also defining the flux from the specific intensity and seeing in these different directions, do some calculation, and then also move over to the pressure of radiation. That's it for today. See you on Friday. Thanks. So we will continue with our description of flux now in detail. Using this, that it is then the energy density, okay? How much energy density is carried, the net rate flow of energy. So you have to multiply it with the speed to get the proper flux. Compare it also to the mass flux. Here it's the radiation energy density times that. But then also it has a direction. So we add a general direction n hat vector describing a unit vector in the direction of the flow. But from this, you know, if you remember how we used to set up our energy density, if you don't, you go back and you look in your course book, you look in your notes, then, okay, but then we know that the C there will cancel, but now we will have an n hat, so this will actually be I nu n hat delta nu delta omega. So then we get it in a certain bandwidth, certain solid angle. So if we want the total now, we integrate. So we can define the radiation flux vector as then integral over all solid angles, integral over all frequencies, I nu n hat d nu d omega. Sometimes we will make the assumption that, okay, we can integrate the frequencies over all intensity. So sometimes we'll say, okay, yeah, we'll make it simple for us. We're going to use this then, yeah, omega, and then it's just the frequency integrated intensity, of course, n hat the omega. Sometimes we might also, analogous to how we did it in Wednesday, we want to work with the frequency at a specific frequency, not the total integrated flux. For example, in observations of astronomy, this is critically important, right? Because it's very difficult. You take an observation of an astronomical object, but you don't get all the frequencies from your telescope. We discussed this already. Perhaps you're tuned to a little band in the optical, you know, where we see. Perhaps you're tuned in a little band in the X-rays. Perhaps you're tuned in a little band in the radio wavelength or so. So then, of course, this becomes critical because you're not going to be able to integrate over all frequencies, only over a certain amount. Okay? If you use this, then of course it's just this one n hat the omega. So there's our flux. We're going to do now a test so that we get a little bit of a feeling. And this now is essentially in the course book on page 22. I think it should be exercises 222, 223. Okay? Now, we want to do, so we're going to use this now. We're going to say, okay, this is frequency integrated already, frequency independent, so we're going to use this simplicity of notation. And then we're going to assume, okay, that our intensity, which in general now can be a function then of theta and phi, the two angles that go into the solid angle. We're going to say that is only a function of theta, only of the polar angle, okay? Not on phi, it's azimutally symmetric. And then we're going to show that in a Cartesian coordinate system, where you can write the flux as fx and x plus fy and y plus fc and c. Fx equals to fy equals to 0, but fc is not necessarily 0. Okay, first then, of course, we need to know the direction vectors, and that's not something that it's something that you should understand. It's not something that you need to rederive every time. It's in the course book for you. You can also look in your vector calculus notes, and it will be there, right? Remember, we set up our standard coordinate system. Why we put up this like this. We had the area here, or the solid angle. We had the phi angle here. We had the polar angle theta there, okay? And then we set up the solid angle from there as sine theta d theta d phi. Similarly, we can set up the unit vector if the unit vector is nx x hat plus ny y hat plus nc c hat, then nx ny nc. This is just going to be cosine of theta. This is going to be, I have to always look this up, so you see, you don't have to memorize this, you just have to understand the ID. Sine theta, sine phi. Okay. So now we have the information, and now we can actually do these calculations using this basic definition here. All right. So, in general, we said, okay, now we have our flux vector, which is then integral over all solid angles. I, in general, theta phi, and then we have the n hat, yeah, and we have the omega. So now we're going to do this specific case. Fx is then going to be the integral of all theta from 0 to pi, the integral phi 0 to 2 pi. And now our intensity here is not a function of phi, but only a function of theta. Our x here, x hat is sine theta, sine phi. And then we have a sine theta, d theta, d phi in the omega. Now, what we can, of course, the only point to realize here now is that since this is only a function of theta and not a function of phi, we can separate the integrals. So this is then theta 0 to pi I of theta sine squared theta d theta times the integral of phi 0 to 2 pi sine I d phi. What is this integral? Yes? Excuse me? This, you mean? It's f. I took x and I used y. Thank you very much. This is what I meant, that you have to keep track of my algebra. Because in x, there's a cos phi. There is not a sine. That would be y. So either we change this to y, or we change this to cos. I'm going to change this to cos, because otherwise I start with y and go to x, so that's more. Yeah? Okay. The question is the same. What is the integral of this? Hopefully we know this. So there will be integrals in the course that we will have to do. And if they're of this type, I expect you to know them. If they're on a more difficult type, I do not expect you to actually know them. Then you will have like an integral solution, kind of like what you get in a mathematics handbook. But if it's x squared or if it's cosine of phi, I do expect you to know that integral. That's just to set the stage there. I mean, this is sine, yeah? That we know, okay? So then if we look at this, what is sine phi 0 to 2 pi? That is 0 minus 0 equals to 0. So this integral is 0. So fx is 0, okay? Since it's the first lecture that we're doing this type of integrals, we're going to do fy also. You know, hopefully you can already now figure out what it will be like. Fy is then theta 0 to pi, phi 0 to 2 pi, I, again, only a function of theta. And then we have now the one that I used before, sine theta, sine phi, and then we have sine theta, d phi. We can again split the integral. So I of theta sine squared theta d theta, phi 0 to 2 pi, and now we have the sine phi d phi. Now, can anybody guess what this integral is? Minus cosine. Yeah. Minus cosine of phi 0 to 2 pi. You do that integral. 0. Flux in the y direction is also 0. So now we're going to do this in the c direction, okay? So for the contrast, I'm going to take away this x. If you haven't had time yet, you know that it's just analogous to the y here, okay? Because of the camera and stuff like that, I can only work on one blackboard. That's, that's why it becomes a little bit like this. All right, let's look at the flux in the c direction. What do we have? We have the integral of all solid angles now, again. We have the intensity, again, only a function of theta. We have n theta the omega. So that's theta, 0 pi, that's phi, 0 2 pi, that's I of theta, and theta is cosine of theta. Then it's sine theta, the theta, the phi. Again, this is not a function of phi. We do not, so we can split the integrals from theta 0 to pi, I of theta, cosine of theta, sine theta, the theta, integral phi 0 to pi, but now we don't have anything there. And as you can see, and this was the whole thing, right? Now suddenly in the c direction, this is not 0 anymore. So this becomes 2 pi theta 0 to pi I of theta cosine of theta sine theta d theta. Okay? Here I will already now add a point that often in the literature, often in our course book, you will see this expression here, not expressed in theta, that's okay, you can do it that, but often using a variable substitution. That variable substitution is mu equals cosine of theta, such that the mu, the theta is minus sine theta. And the limits here, theta equals to 0, then is mu equals to 1, right? And theta equals to pi is mu equals to minus 1. It's just the cosine. So with that variable substitution, you see that you can write this expression. So mu then going from 1 to negative 1, I, and there we can just change I mu theta. Here we have to be a little bit careful. This is just a mu, right? And this sine theta, the theta, is going to be minus d mu. So we can flip the integral there to write this as 2 pi mu minus 1 to 1 I mu d mu. Okay? And this is often then what you see referred to as the flux in a lot of astrophysical textbooks also. We'll come to in a few minutes why this is often then referred to as the flux. well, the other ones were 0 if the radiation field was only a function of mu, right? So we can already understand that. Yeah. Of course, the other ones are not 0 if the radiation field is also a function of the other angle, the azimuthal angle, okay? Then you cannot say that this is the only flux that matters. Then you have to consider the vector nature of the flux. Okay, so we're going to do one little more tour on this. That's okay. So now we have, in case I of, in principle, theta phi equals to I of theta, then we know that fx, fy equals to 0, but fc is not necessarily 0. Okay? What if now I of the head is just I? That is, it is isotropic. And this is what I was referring to now. Your pencils of radiation in some n-naught direction there, there, and there is actually not dependent on direction. So schematically, we have as many of them there, as many of them there, in there, there, in all directions. What happens then? We have already talked about the answer. Intuitively, the flux is 0, right? And we have already shown that in the x and y, when we have vector composed the flux in x and y, they are 0. We just now need to show it in the z direction as well. Where it was not when we had a directional dependence on the intensity. Okay. Let's see then what happens in this expression. We can use this one now to get used to also the mu notation. We know that in this case, Fc then is 2 pi, and it was mu going from -1 to 1, I mu d mu. But if this is now not the function of mu, we can take it outside integral. I hope we can agree on that. 2 pi I. Then we have mu -1 to 1 mu d mu. And here you see the nice thing about putting it in this space, because now we get an algebraic integral. Yeah? And this is an uneven integral on an even interval. What do we know about such integrals? They're 0. We can even algebraically understand this, right? In this case, it's from -1 to 1, right? On the x-axis here, okay? So if we go from there to there, you see that the area here and the area there just cancels each other. And that's a general nature if you have an uneven integral over an even interval. I say this now 2 times because it's actually something we will continue to use several times. It just eases. So, yeah, okay, this is 0. So indeed, now we have shown this, that we sketched out schematically that if you have an isotropic radiation field, which in our description means that the specific intensity is directional independent, you get a 0 flux from that. Interestingly, let's see what happens to the energy density. Intuitively, what do we think? If we have an isotropic radiation field, will we also get a 0 energy density? Remember, the energy density was referred to as the mean intensity as well, right? It's a mean property. So it's not a net difference like the flux. The flux works with a difference. It's that minus that. But if you take an average, a mean intensity, an energy density, then you just add them up and average them in all directions. So what would the intuitive answer then be? That the energy density should be? Well, the mean intensity should be then, if it's directional independent, it should be the same, right? So the energy density will then also not be 0 in that picture. So let's look at that. We can set up then that our definition of the energy density was 1 over c integral over all solid angles I the omega. But now I have said that this I is not a function of theta. It's not a function of phi. Thus, it's not a function of omega. So we can directly set this out such that it's I divided by c go there. And this one we did. That was the integral over the full sky. So this is just 4 pi I divided by c. So it's not 0 like the flux for an isotropic radiation field. Okay? Now, if you look at the definition of the mean intensity, I taught this, you can hear, right? So the mean intensity is often defined as J, denoted by J. It is defined then as the 1 over 4. So, well, it's easier if you do it like this. The integral of I, which in principle can be a function of theta or phi, the omega, and then we average this over all omega. So this is an average, a mean. This we know is 4 pi, so it's just I, the omega, divided by 4 pi. But if this now is directionally independent, we can directly take it outside the integral such that this is just the omega divided by 4 pi equals to I. So in the case of an isotropic radiation field, indeed, as should have been intuitively clear, the mean intensity is equal to the intensity. The energy density is not 0, but the flux, which is a directional dependence, is 0. Next week, we will introduce the pressure of radiation, which also is one of these moments, one higher order moment, but it's also a mean. So similarly there, we should not expect it to be 0. It's the uneven moments that we expect to be 0. In the case of an isotropic radiation field. I go through this now generically, but keep in mind the black body radiation when you hear this isotropic radiation field, because that's going to be our main application. And indeed, we're going to introduce it first, but actually later during the course, once we have gotten to that point, we will actually look at even Planck's original derivation of the black body radiation and discuss a little bit how he came up with that, which was a mathematical trick based on empirical findings. Specifically, that if you do not take that into account, you end up with what is called the ultraviolet catastrophe. The ultraviolet catastrophe, we will see next week, has to do with that in the classical sense. When you calculate the radiation energy density of an isotropic radiation field in equilibrium, classically, you end up, when you frequency integrate, that it's infinite. Okay? And that is, of course, an absurd result. We know that we cannot have infinite radiation energy density coming out, for example, from every human. That would be a little bit much. So that was the so-called ultraviolet catastrophe of classical physics, which led him to his well, first empirical law, and then the mathematical trick, and then the hypothesis of the quantum oscillator. But that's for later in the course. Now I wanted to go back to this case where we indeed had this description of the flux, only in the z direction, in the vertical direction, x, y, 0, when the intensity only was a function of the angle theta and not phi. So we can sketch this out a little bit to get a feeling for what it's about. So you have some sort of situation now, imagine, where you have a vertical here, in z direction, and perhaps we're an observer sitting far, far away, somewhere there. Then you have your system here, and that has some plane parallel layers, like this, and so forth. Okay? And here is your x and your y. And then we have said that, okay, the intensity, when you have a ray here now in some n hat direction, okay, then the intensity can be a function of this angle theta. That's what we said in this. But we said that I, in general, it can be a function of theta, can also be a function of phi, because of course, here you see this is a two-dimensional drawing. Now you have to think in and outside the board. This goes just in that direction, but we can tilt it in the board or we can tilt it out the board. And typically what we do then is that we project it down and do like this, and then we have the phi angle here. So essentially what we're saying when we're saying that, okay, we're going to skip this, and this is just going to be a function of theta, we're saying that it's isotropic in this cone here. Okay? We tilt it in and out like this. Okay? So that what it means would be in axis symmetric in this case. It's independent on the phi angle, it's only dependent on the theta angle. And this you can show is the case for systems where the variation of physical variables, such as the density, such as the temperature, such as the velocity, which we can use to describe a gas, an astrophysical gas normally, is dependent only on the height and not on these directions. That is, that if you take a layer up here, then you can have a certain value of the temperature or the pressure. You take a value down here, then you have another, and those can be different. But if you take 1 point there and 1 point there on the same height, then they will be the same. They will have the same density, the same temperature. So the variation is in the vertical direction. Again, in astrophysics, the most simplified, the most intuitive example of this is, of course, a star, which is to a certain degree spherically symmetric, and the variation goes from inside out or outside in. For example, the temperature in the core of a star is much, much higher than the temperature on the surface of the star. But if you at each layer of the star make a big circle at a certain radius, then the properties are roughly constant on that circle. This is a zeroth order approximation because, of course, there can be flows and stuff like that that disturbs this. Okay? The same thing here on the Earth can be thought about our atmosphere. We discussed this. If you think about the pressure, perhaps easiest, right? We take it here, where I'm standing, then it's going to have one value. But we know that if we go up on a mountaintop, not so easy in Leuven perhaps, but use your imagination, then the pressure is lower. I think this is something that we all intuitively know, right? However, if I just go from here and I stand on the other side of the room, then the pressure is roughly the same. Yeah? So the atmosphere of the Earth works in the same way. At a certain height, it has more or less constant values, but when you go up, then they change. And if this is the main property, then the approximation for the specific intensity is that it's axisymmetric. That is, the phi angle, it doesn't depend on phi, it depends only on theta. And therefore, the fluxes in this direction cancel out, which is also intuitive because the properties are the same here as there shouldn't be any net flows, right? Yeah? But if they're not the same there, then there is the net flow. Yeah? This also goes with, we're seeing a net flow coming out, photons from the surface of the sun, right? It's a gigantic leakage of photons from the surface of the sun in the radial direction outwards, primarily. Okay. So let's see if we can use this in a little bit more discussions of the flux here. So we can see now that, okay, let's look now at the surface of an object, say a star. Then we have this direction from the surface and C. And then we have a radiation field. Now, then we have our n hat vector and we have the theta angle. I'm going to assume the axis symmetric, so there's no phi dependence. So if we're on the surface here of the object, not in the interior, but on the surface, then okay, we can approximate. Imagine that you're on the surface of the sun. There is a lot of photons coming from beneath, right? Yeah? But from outer space, there isn't any coming. Not in comparison. There might be something small, you know, hitting the sun surface, but basically nothing. Okay? So on the surface there, where the photon leakage is from, yeah, you can basically, well, okay, all the radiation is coming from beneath, you know, from all these directions. And then it's slipping out. But from outside in, there is nothing. And that, what do we mean? Okay, then we can say that, okay, we can have photons coming from beneath in all angles from theta 0 to 90 degrees. That would be there, right? There we have the photons leaking out on the surface of the object. Yeah? That corresponds then to mu angle 1 to 0, and we can call that I plus in our notation. Now, these angles, that would be then the direction vector going this, and so forth. Yeah? Those go down. That's the radiation then coming from outside in. And on the surface of the object, we said those are negligible. So those we can set to 0 in the absence of another external object. Now, for example, if you take, there are occasions, important occasions, where this is not true. For example, if you have a binary star system, then of course the radiation from the other star will hit you on the surface if you're close enough. And then you cannot apply this. Okay? That's just one example of this. Yeah. But then we can say, okay, on the surface here, for the mu angles, that is from 90 to 180, right? There to there. That's the phi from 0 to -1. Then we have I minus, and that's actually 0. Okay? So now, if we set up our flux expression, which was Fc 2 pi mu minus 1, 1, and then we had I, which is a function of mu, mu d mu. So let's do an extra step here. That would be then I plus I minus mu d mu. And where am I? Right. We have said that there's no incoming radiation, so this is 0. So then we see that the Fc here is really 2 pi mu. Be careful with the limits, because now we have only outgoing radiation, right? So that's just 0 to 1 I plus mu d mu. And then we can see, okay, can we estimate now what the flux is going to be for a given specific intensity? And we can do this with various approximations. In general, when you try to calculate now what will be the emergent flux from an object, then you might have to solve the full radiative transfer equation with some numerical method. And then you have a certain function of mu, and you have to integrate this to get out the total flux, right? But there are various approximations we can use. The simplest is, of course, to say that, okay, it's just leaking out the same in all directions here. Yeah? That's one. Okay? Then we can just do this integral immediately. If it's if I plus of mu equals just I plus, so it's not a function of mu, then we can say that Fc is just 2 pi I plus, and then it's just that, which is just divided by 2, so it's pi I plus. Yeah, hopefully you know that integral. So then we see that the flux is just pi times the intensity. So that's how you relate them, yeah? That is, again, not true, because if you're in, it's not true inside the object, because there you have incoming radiation. So then you, of course, have to then take into account the negative, the ingoing directions as well. But we made the approximation that at the surface, you're only leaking outwards. You don't have any incoming. Another thing that we will use in chapter 3 is that, okay, under certain approximations, you can set this up as an analytic function of the angle here. For example, you can assume that it has a linear dependence. Say that a plus b mu, where a and b are two constant, and it depends on mu. And then, of course, you can solve the integral again. And that is what is called the Eddington-Barbier approximation. And we will use that in chapter 3 to explain, for example, a phenomena like limb darkening. What is limb darkening? Well, it is that when you look at astronomical objects, most famously the sun in the optical, and you can just, look this online if you want, just limb darkening sun, and then it will come up. Then you see that on the central portions of your image, they will look brighter than on the limbs. That's why it's called limb darkening. So the limbs from the object actually looks darker than the central portion of the objects. And we're going to use this law to explain that phenomena then, with a certain functional behavior. Okay, and then we're going to relate it also actually to the physical reason why this is, which in the sun's case has to do with the temperature, the vertical temperature dependence here. and the layers from which the radiation is actually escaping when you look in the central parts versus the limbs. And we'll come to that again in chapter 3. This is the basic mechanics that we use to describe that phenomena later. The radiation pressure, or in its general form, the radiation energy stress tensor. So, the first thing to realize, so to say, about radiation pressure is that it's actually fully analogous to gas pressure. It is, in that sense, the pressure of a photon gas. And as such, it is also useful here then to consider this little photon fluid picture when we set up a basic definition for our radiation pressure. So we can have a quantity here which will be our photon density. Now that photon density then is essentially just the number density of photons. So photons per unit volume. So that will then be the energy density of the radiation field divided by the energy of a photon. So h nu. Okay? And then we can just look at our definition, which we got last week for the radiation energy density in terms of the specific intensity, which was this one. And we can then just identify that the photon density here now is going to be then this divided by h nu, so just 1 over c I need either the C there or the C there, which you can also then just write as at this one, where then our I nu is just I nu divided by C h nu, and that's the photon density per frequency, per solid angle, or then, per steradian. Okay? So fairly straightforward. We will also use this then when we discuss equilibrium black body radiation, because we can just use them in order to get a feeling for the number of photons contained within a volume of black body radiation. Now here, though, we're interested in the pressure, which is technically the normal component of the radiation momentum flow. Okay? Remember that we had this the first week. Photons carry a certain energy h nu, or if we prefer, hc divided by lambda, but they also have a momentum given by E divided by C. So apologize here now for the double notation in sense of the total energy density and the photon energy there. It's just standard, unfortunate. Hopefully it's always clear from the context. So this is just h nu divided by c. We should have skipped this. It would have been clearer. And that's then now the photon momentum, which of course goes in a certain direction, because it's a momentum. So you have a photon momentum h nu divided by c in some direction n hat, as we had before. And you have the photon flux, the photon number flux, which is a flux. However, now with the number density, instead of previously, we had the radiative flux, which is an energy flux. So now it's just this. So phi nu per, now again, unit solid angle and per frequency times c. So then this photon momentum flux, okay, you can look at how this is related to a pressure by considering the pressure as a force per unit area, okay? But that is, of course, then the momentum per unit time times area, okay? So then you can immediately realize, remember last week when we talked about the radiative flux as the energy per unit time per unit area. That was the radiative energy flux. That's why we can call the radiation pressure the radiative momentum flux in the same way. So again then we have to specify a direction which this goes. So you can have an area here, say, with some normal, and then you can have this momentum flux acting in a different direction, okay? So this would be the momentum flux in some n hat direction. It should not be parallel. And this is then the normal to the area, which is, of course, an imaginary area in space now. Of course, if they're in the same direction, then you have the direct normal component of the radiation momentum flux, but in more generality, you will have to decompose this in its three vector components and then split up there. And that is how you also build up stresses. And the analogy then with gas pressure is indeed the same. If we have static gas pressure, we actually have then an isotropic pressure tensor, in this case, with components only along the diagonal. However, if we have, for example, a liquid in motion, we can have shears. Yeah? Such shears then causes stresses in the same way as here, and that is then called viscosity. If you have ever seen, for example, a YouTube video on a viscous fluid, you will know what I mean. These are then the shear stresses. By analogy, we can actually then also have photon viscosity. Okay? Now, it turns out that for most situations, such photon viscosity, and one can realize this by dimensional analysis, for example, is normally not as important as standard viscosity. That being said, there are instances where you might have to take this into account. For example, in very luminous accretion disks around supermassive black holes. There are some discussions whether photon viscosity might play a role. Now, normally though, what is important is the difference in the different components along the diagonal of the radiation pressure tensor. And this is something that we will discuss further on now. So, from this, we can define our radiation pressure tensor here. We have this in now some direction Ni. The normal we put in Nj here. We could have just tilted it and put the surface in this direction. Then it would have been along another coordinate axis. We have to specify this is the important, and this is not necessarily in the same direction, such that the ijth component of the radiation pressure is this. And then we have the photon flux as h nu Ni Nj d nu d omega, whereby we can use that definition up here in order to realize how to put this in our basic quantity of the specific intensity. And we can also realize here that, okay, we can actually put this already now in so-called dyadic notation, like this. So this would be the radiation pressure tensor. I nu divided by C hat d nu d omega. Where, for example, if you put this on a Cartesian coordinate system, you will, of course, get pxx, pxy, pxc, pyx, pyy, pyc, pcx, pcy, pcc. So, to get a little better feeling for this, we will discuss a couple of examples next. We will do the same example as we did with the radiative flux. Yes, please. Sorry? We will come to actually now when this is the case and when this is not the case. when you have what I called photon viscosity, then the non-diagonal terms are non-zero, okay? And that happens in fully three-dimensional media. Like I said, typically those terms are small. They're smaller than the corresponding gas viscosity terms. Often. It doesn't always have to be like that, but in most situations. It is also always symmetric. So if you know, there are only 6 independent components at most. Okay? Now, just like when we discussed the flux, however, you will almost always have this referred to as the radiation pressure. Just like we talked about the radiative flux, which was then implicitly the flux in like the vertical or the radial direction most often. Even though we discussed to some length that technically flux is a vector with a direction, technically radiation pressure is a tensor. However, for most situations, we can identify the CC component in a Cartesian here, PCC, with just, we can call it P, and that is typically what we call the radiation pressure. Now, for completeness, though, I introduced it generally, and we will also now just go into some cases where this is the case. Okay? So specifically, we're going to take the same illustrative example as we did for the radiative flux. Okay? For simplicity, we're going to work with the frequency integrated intensity. That's a notational thing. Yeah? So we're working with this quantity now. Okay? And then we're going to say that this quantity, which in general, as we have seen, is a function of 2 angles, theta and phi, but we're going to say that it's axisymmetric. That is only a function of theta. Go back to your class last week if you don't remember this from the radiative flux. That's how we could identify that in these situations, the flux in these directions indeed cancel each other. They were 0. We were left with only a net flux in that direction. So now we're going to see what this does with the radiation pressure tensor. Specifically, we're going to show that you can write it in Cartesian coordinates again in this form. E minus P divided by 2, E minus P divided by 2, and P, where indeed now I identified PCZ with P, and as was pointed out from the audience, the off-diagonal terms are 0 in this case. So how did we now come to this conclusion? Okay, so I'm going to do 1 or 2 steps for you, and it will then be an exercise for you. It is included, the full solution in the exercise set, to complete this, okay? The way you can realize this is that, okay, we have this, and I've expressed it now as the PCC component, but also the radiation energy density. Now, the radiation energy density, we know what definition it had. It had this, I divided by C, the omega. We have said that I is only a function of theta, not of phi. Okay, and then I'm just going to skip ahead the steps because we did all of these last week. So this is 2 pi divided by C minus 1 to 1 I of mu, where the mu. Okay? Where, again, we remember that mu is cosine over theta angle. Now, similarly, we can do the PC component as, then I'm going to write it out now, phi 0 to 2 pi, theta 0 to pi, okay? Then we have our I theta divided by c, and then we have to fill in for the radiation pressure tensor in the CC direction, NC, NC. Okay? And now we have to go back to our lecture notes again to identify what was NC. It was cosine of theta, remember? So therefore, in that direction, we have a cosine square theta. Okay? And then we had the solid angle, which is sine theta, d theta, d phi. Again, this is why I said that it's good if you get used to these type of integrals, because they come back all the time. All right, so this is the PZZ component, and again, we can see since this is only a function of theta now, we don't have any phi dependence, we can just take that out, so this is then just 2 pi divided by c, and now we have, I changed to the mu angle, plus I of mu squared d mu, okay? And following this, we just call this P. Okay. Yes. Okay, now let's look at the XX component. So, Pxx is going to be then our phi to 2 pi, our theta goes to 0 to pi, okay? I of theta divided by c, and now I'm going to do the extra step here, nx, xx component, sine theta, d theta, d phi. So then we're going to have to look in our lecture notes. What was this nx? That is the unit vector, x direction. It was sine theta cosine of phi, and then we have two of them, so squared. We have a sine theta d theta d phi. Okay, we can separate these integrals, right? Because again, I is only a function of theta. And this is where the complication, of course, comes in when I is not only a function of theta. Then you cannot separate the integral, so you cannot solve this integral independently. And that's indeed why you can also then end up with off-diagonal terms. Now here we can. So we're going to have phi 0 to 2 pi. And then we have cosine squared phi d phi. And then we have another integral here, which is a sine cubed. So that is then theta 0 to pi I of theta. I put the c down there. We have the sine cube d theta. Okay, so I make this note also about the integrals, because I told you, like, for example, in, say, an exam situation, if you get an integral like sine theta or x, I expect you to know that. This is actually not a really trivial integral to solve. Yeah? So this I would actually give you some hint. How do you do this? Well, in this case, perhaps you might want to use the trigonometric identity that this is indeed equal to 1/2 1 minus cos 2 phi. Okay? So if we do this now, and we just save this, we call this integral y, then we can see that indeed this one here is going to be, well, it's 1/2 there, right? And this is going to come out as a sine, so I didn't even need to do the extra step, if I'm going to be honest, because we can do this in our heads. We know that the cosine becomes a sine, right? And we have 0 to 2 pi as an interval, so we should immediately realize that this is going to be 0 no matter what we do. So then we're just left with that, and that is 1/2, so that we can integrate. Yeah? So that's just going to be then 2 pi and a half, so we get out a pi. So in the end, we're just left with pi times this. And now we do our variable substitution, so we have pi divided by c, mu minus 1 to 1 I of mu, mu squared d mu. And now you should immediately realize, didn't you do an algebraic error there? Did I? I did. This is a sine. So it is this. Okay? If you see this, immediately shout out to me, okay? So we have can split this integral then into 2. Pi divided by c, the integral minus 1 to 1 I of mu d mu minus pi divided by c minus 1 to 1 I of mu, mu squared d mu. And hopefully now, and realizing this, you will see why I did that substitution. I'm going to try to keep this here now and stick to my one board. This one, you see that, okay, it looks quite a bit like this, the energy density. And here is where the angular moments come into play. Keep this in your head. Energy density is the 0th angular moment. So when you see this and there is nothing there, then it's like this is something like the energy density or the mean intensity, which is the straight one. Yeah. When you have a first moment here, then it's a flux-like quantity. It can be the Eddington flux, it can be the flux. And you see something like a squared here, a mu squared. Yeah. Then it's like a pressure-like quantity, or Eddington's K, a useful mnemonic. So we had that the pxx component, indeed there we had pi, and here we identified this with e there. It's e divided by 2. As you can see, the second there is minus p divided by 2. And this is what we had there. Okay? So, your task in your exercise then will of course be to verify the PYY and also just take one of the off diagonal. Take one of them and just show that in the case that this is a function only of theta, they will be 0. If they're not, then I've done an error and you come back to me and tell me what I've done wrong. Okay? So that's the task here. Now we're going to look at this a little bit once we have done the mathematics of it and understood a little bit how we can connect the energy density, the scalar radiation pressure component, the PCC, the PCC component, and look at some cases. Again, it's understood here that P is PCC. Okay. First, okay. Let's take the trace of this. You take the trace of your tensor. That's just summing up the diagonal. Then you can see that it's E minus 2 divided by 2 plus E minus P divided by 2 plus P. That's just E. So that's interesting. And that's actually generally valid, not just for this case where we had I as only a function of theta, so no phi dependence. This, that the trace is always the energy density, that is generally true. And you can see this again by going back to the definition. Because these are unit vectors, which means that their scalar product is 1. If the scalar product is 1, we end up with this. This is the definition of the energy density. So this will be the case regardless of the dependence of the radiation field, even in a non-axisymmetric situation. Now, what you can also see is that in order to get an isotropic pressure, like we normally think of the gas pressure as being an isotropic pressure, to get an isotropic radiation pressure, there has to be a certain relation between the energy density and the pressure. Yes. Exactly. You have to have that 3P equals to E, where P again is CC. Because if you plug in 3P here and there, yeah, then you get P, 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 diagonal. When this is not the case, then you don't get it. Okay? For example, if P equals to E, then you can see that, well, then we have the situation that it's 0, 0, and P equal to PCC, right? Now, we will come back to both of these cases, actually. This is the case for an isotropic radiation field. It is the case for equilibrium radiation described by blackbody radiation. Okay? This is the case for, say, the opposite direction, where we have a fully pointed source of radiation. For example, very far away from the star, you can say that the radiation field coming from the star then, and just going out in the space, has become radial. Remember, we sort of hinted toward that the last week already, that the angle subtended by, in this case, the star, well, if we look at the sun outside, it's kind of like this or something like that. But the further away I go, the solid angle that, or the angle the sun will subtend is going to be smaller and smaller and smaller until it appears as a point source. And then the radiation field is radially directed. We call it to be radially streaming. And then we can also show that in this case, P is actually E. So then we get this relation. This has actually consequences for example, when we use later on the moments equation, that is the energy and the momentum conservation equations of the radiation field, to derive also a wave equation, in order then to get the correct wave speed in the vacuum limit, which should be then the speed of light. Yeah? We have to apply this. Whereas in this case, if we do this, which we will do as an exercise as well, we will get a wave speed which is c divided by square root of 3. Now, nicely enough, we can actually identify that wave speed with the sound speed in the early universe. When the universe itself was completely radiation dominated, then the sound speed there can be derived by this, and it's in the limit that you can completely neglect the matter. It's indeed c divided by square root of 3. And to a first approximation, this is indeed what such sound waves are, what is imprinted on the cosmic background radiation that we see coming through us today, when it was first released at what is called the era of recombination. And if all of these terms are completely unfamiliar to you, that's fine. We will actually discuss them throughout the course when we come to that application.